Today, we're going to explore a key concept in structural engineering, the critical buckling load of a steel column. Let's walk through a practical example to understand this better. To recap, we'll be using the following steps to solve this problem. 1. Locate the relevant equation. 2. Calculate column properties. 3. Solve for the unknown. Imagine we have a steel column. This column is 10 feet long and it's unbraced, meaning there's no lateral support. It's also pinned at both the top and bottom, which affects how it will respond under load. The column's cross-sectional area is 18 square inches, and its moment of inertia, a measure of how its mass is distributed, is 30 inches to the fourth power. Our goal is to find the critical buckling load for this column, expressed in thousands of pounds per square inch, or KSI, and we'll round our answer to the nearest whole number. To solve this, we'll use Euler's formula for column buckling. This formula is a fundamental tool in our field, and it's found in the NCEES handbook under the section on columns. The formula states that the critical buckling load is equal to the square of pi multiplied by the modulus of elasticity of the material and the moment of inertia of the column's cross-section. This product is then divided by the square of the product of the effective length factor and the length of the column. Let's look at the given data. For our steel column, the modulus of elasticity, a measure of the material's stiffness, is 29,000 KSI. The effective length factor, denoted by the letter K, is 1, since our column is pinned at both ends. This factor affects how the length of the column contributes to its tendency to buckle. Now, let's apply these values. But first, a critical step: unit conversion. Our column's length is given in feet, but we need it in inches for our calculation. So, we convert 10 feet into inches, giving us 120 inches. With these values, the formula now tells us to multiply the square of pi with 29,000 KSI and 30 inches to the fourth power. Then, we divide this by the square of the product of our effective length factor, which is 1, and our converted column length, 120 inches. After calculating, we find that the critical buckling load is approximately 596.3 kips. Remember, a kip is 1,000 pounds. Rounding this to the nearest whole number, we conclude that our critical buckling load is about 596 kips. This figure is essential for us as engineers. It indicates the maximum load our steel column can withstand before it becomes unstable due to buckling. This understanding is crucial for designing safe and efficient structures. To wrap up, today we've taken a real-world problem, applied Euler's buckling formula, considered the specific properties of our steel column, and navigated through some unit conversions to determine a critical safety threshold. This is a great example of how theoretical knowledge is applied in structural engineering.